Hello, in this video I'll be working through your Day 1 homework assignment, which is a review of functions. For this first problem, we're trying to identify the name of the function family that matches the general equation. Equation A is a linear function. We can write linear functions in different ways. This linear function is in point-slope form. So point-slope form. The point being x sub 1 comma y sub 1, and the slope being a. Equation B, this is a quadratic function. And like linear functions, there are several different forms that we can write quadratic equations in. This one is in standard form. Standard form makes it easier for us to identify the y-intercept. In this case, the y-intercept is 0, c. Equation C, assuming that b is a positive integer, this is a power function. Equation D, this one we could call it by a few different names. I'm going to call it the greatest integer function. We could also call it the floor function. It's a function that rounds down. So for example, if we put these brackets with the little feet on the bottom around the number 3.2, we would round that down to 3. We round it down to the greatest integer that is less than or equal to that number inside the brackets. So the floor function is a good name for this, kind of helps you remember to put the feet at the bottom of the bracket. If the little feet were at the top, maybe we wouldn't call it feet in that case, but if it were at the top of the bracket, then we'd call that the ceiling function. That would be the least integer function, and that would round up. Equation E, you may not have encountered this one before. This is called a logistic function. Logistic functions are good for modeling population growth in a situation where you have some kind of carrying capacity for your population. Equation F is an inverse function. Equation G is a constant function. A constant function is a special type of linear function. It's also a special kind of polynomial function. Equation H is our polynomial in standard form. I, we could call this by a few names as well. This is a sine function. We can also call it a trig function or trigonometric function. Or more generally, we can call it a sinusoidal function. And equation J, this is a linear equation in standard form. Equation K, this is an absolute value function. With the vertex at the point h comma k. L, so here we have a fraction where p of x and q of x represent polynomial functions. So this one is called a rational function. Rational, assuming that p of x and q of x are polynomials. Equation M, this is a radical function. Equation N, this is a linear equation in slope-intercept form. Slope-intercept, probably the first type of linear equation you worked with. Now, when you first learn linear equations, oftentimes we teach that it's in the form y equals mx plus b. In that case, b is the y-intercept, m is the slope. But pay attention to the way this one is written, a plus bx. The b here is the coefficient of x, so that is actually the slope in this case. And the a would be your y-intercept. So it doesn't matter what we call the letters. We have to look at if it's the coefficient of the linear term or if it's the constant coefficient to determine whether it's that slope or y-intercept. Okay, equation O, this is a logarithmic function. Equation P is a quadratic function. And this quadratic function is in factored form. Q is our piecewise function. Equation R is exponential. F is another quadratic function. This one in vertex form. And equation T is our reciprocal function. Okay, for problem 2, part A, this is an exponential function. So it's going to be of the form y equals a times b to the power x. And we have a couple points labeled on our graph. We have the point 1, 2 and 2, 4. So we can solve our exponential equation by substituting these values in and solving the system of equations. So if I have something of the form y equals a times b to the power x, in this case I know that when x equals 1, y is equal to 2. So 2 equals a times b to the power 1. I also know when x is 2, y is 4. So 4 equals a times b to the power 2. And now I'd want to solve this system. I have a few ways I could do that. I could solve by substitution. Could solve one equation for a and then substitute that into the other equation. Or I could try a linear combination where I divide the left-hand sides and divide the right-hand sides. Personally, I find the linear combination method easier. Some people like substitution. Either way will work. So I'm going to do equation 2 divided by equation 1. I'm going to divide the left-hand sides. 4 divided by 2 is 2. When I divide the right-hand sides, ab squared divided by ab, the a's cancel out, and b squared divided by b leaves me with just b. So now I know b equals 2. Then using substitution, if I know b is 2, this becomes 2 equals a times 2, therefore a has to equal 1. So now a is 1 and b is 2. So my equation is y equals, if a is 1, I don't need to write the 1, b is 2, so 2 to the power x. That's my equation for this particular exponential graph. The domain for my function is all real numbers. I'm going to use interval notation, or you could use the symbol for the set of all real numbers. The range for this function is not all real numbers, it's all real numbers greater than 0. So in interval notation would be the open bracket or parenthesis 0, infinity. For part B, we have a quadratic function. And we're given quite a bit of information. We know the vertex is at coordinates 1, -1. We also have our two x-intercepts, -1, 0 and 3, 0. So we could write our quadratic equation in vertex form pretty easily, or in factored form pretty easily. It would take a little bit more work to do standard form, but we could do that one as well. So you get to decide which form you want to try and write your equation in. I'm going to go with factored form. So factored form in general is going to look like y equals a times the quantity x minus c times the quantity x minus d, where the c and the d are my x-intercept values. So I have y equals a times x minus -1, or x plus 1, times x minus 3. And now all I need to do to solve for a is to substitute in another point, x comma y. So I could use the vertex, or I could use this point over here. I've got 5, 3. Let's do that. So I know when y is 3, x is 5, 5 plus 1 is 6, 5 minus 3 is 2. So 3 equals 12a. Now if I divide both sides by 12, I get a equals 1/4. So I know my equation is y equals 1/4 times the quantity x plus 1 times the quantity x minus 3. There's my equation in factored form. If you chose to write your equation in vertex form, that a value would still be the same. So it would be 1/4 times the quantity x minus 1 squared minus 1. Now the domain for our quadratic function is all real numbers. That's always true of quadratic functions. And our range, in this case, goes from the vertex at -1, including that -1, up to infinity. So we need a closed bracket to include the -1, or a square bracket. Part C, this time we have an absolute value function. So in general, our equation is going to be of this form: y equals a, absolute value of x minus h, and then plus k, where h and k are my vertex. And I can see on the graph that the vertex occurs at 2, 4. So that's my h is 2, and my k is 4. So y equals a times the absolute value of x minus 2 plus 4. Now I can use any other point on this graph to help me solve for a. So I have the point 3, 2. Let's use that one. When y is 2, x is 3. So the absolute value of 3 minus 2 is 1. Absolute value of 1 is just 1. I didn't really need to write that. Plus 4. And if we subtract 4 on both sides, we get -2 equals a. So my equation, y equals -2 times the absolute value of x minus 2 plus 4. The domain for this function, all real numbers. And the range, we need a closed bracket around the 4, but this one goes from -infinity up to 4. So we start at -infinity, open bracket, and then closed bracket around the 4. Part D, this graph is logarithmic. And I know what the parent log function looks like. It has a vertical asymptote on the y-axis, so that hasn't changed with this graph. I also know my parent log function has an x-intercept at 1, 0. That has not changed on this graph. So in terms of transformations, there's not a whole lot happening here. And this point e, 1 is a really big clue about the base of my logarithmic function. So you might take a guess, since we have the log of my x value here equal to 1, that the base is probably e. And in fact, if we just write y equals natural log of x, we can check these 2 points and see if it works out, see if it checks out. So when x is e, the natural log of e is 1, so that point is satisfied. And our other point here, this 1, 0, if we substitute that in, the natural log of 1 is in fact 0. So both of these points satisfy this equation. This is the equation of this graph. Part E. Now, hopefully you recognize the shape of this graph. This is a tangent function. Not sure yet if there have been any transformations applied to our parent tangent function. So let's think about key points. Well, we know on our parent tangent function, the tangent of 0 is 0. So that point remains the same here. We also know that the period of our parent tangent function is pi. So pi is approximately 3.14, and it does look like that's this point right here. And that is, in fact, one cycle to the right of this point here at the origin. So it looks like there is not a change of period for this tangent function. It's still equal to pi. And then we also have, on the parent tangent function, we have our first positive vertical asymptote at pi over 2. Now, pi over 2 is just the number pi divided by 2. So on our calculator, we can get a decimal approximation. That's about 1.57. So 1.57 is about right here. So on the parent tangent function, we would have a vertical asymptote here. And on this graph, that does appear to be where this vertical asymptote is. So it does not look like there have been any transformations applied to that parent function. Let's just check pi over 4. We know on the parent tangent function, tangent of pi over 4 is equal to 1. Pi over 4 is the number pi divided by 4. That's approximately 0.79. So maybe about right here. And if we follow that up, that does look like it's at 1. So this is just the graph y equals tangent of x. Now the domain for this graph, it's a little difficult to write the domain when we have so many points of discontinuity, so many points that are not included in our domain. So in this case, it's going to be easier to describe what's not in the domain than it is to describe what is in the domain. So I'm going to say x is not equal to, implying that it's equal to everything except what I'm about to list. So x is not equal to pi over 2, we know that one for sure. X is not pi over 2 because we have a vertical asymptote there. Then we also have a vertical asymptote, a distance of pi away from that asymptote, since the period is pi. Every pi units after pi over 2, we're going to have another vertical asymptote. Likewise, every pi units prior to pi over 2, we're going to have a vertical asymptote. Well, how do we say all multiples of pi added to or subtracted from pi over 2? Well, we can simply say plus pi times k, but we need to be specific about what k is. We want to get numbers like plus 1 pi, plus 2 pi, plus 3 pi, plus 4 pi, or minus 1 pi, minus 2 pi, minus 3 pi, minus 4 pi. So we want k to be a positive or negative whole number. In other words, we want k to be an integer. So say k is an element of the set of integers. And that's my domain. The range for the tangent function, that's easy. The range is all real numbers. Part F. So here I have a trigonometric function. I could write a sine equation or a cosine equation. I'm going to go with the sine equation because I can see if I use sine there is no phase shift. So when I'm writing my trig equation, the very first thing I like to do is identify that sinusoidal axis that passes through the middle. And in this case, it occurs at positive 1. So I know d equals 1. When I say d, I'm referring to this general equation. I said I was writing a sine equation, so it will be a times the sine of b times x minus c plus d. So I've already determined my d value is 1. I've got a plus 1 at the end. That is a vertical shift up 1 unit. The next thing I do is I measure the distance from that sinusoidal axis to the maximum point on the curve. That's my amplitude. So in this case, A is 3. So I have A and I have D. Okay, then I'm going to work on finding the value of B. For that, I need to know the period. And I typically like to measure the distance from one maximum to the next maximum. On this particular graph, that's going to be hard to do because these x-coordinates aren't labeled. We would have to make a guess. So instead, I'm going to find some better points that correspond. This point here on the sinusoidal axis, if I go to the next corresponding point in the next cycle, would be right here at pi. So that tells me that the period is pi. And I know my period is 2 pi over the b value. Or I can say b equals 2 pi over the period. And I already know the period is pi, so now I simplify that and I get b equals 2. So now I have a, b, and d. C would be the phase shift, but there is no phase shift because on the sine graph, to identify the phase shift, you find the point on the increasing part of the function that passes through the sinusoidal axis, and that's this point right here, and it has not shifted. It is still right there on the y-axis, so no phase shift. That means my equation is y equals 3 times the sine of 2x, since there's no phase shift, it's just an x here, plus 1. And this is all, of course, in radians. Now my domain for this function, all real numbers. And my range, we're going to use closed brackets around the minimum point and the maximum point, so from -2 to +4. G, this is a rational function. And I can see that I have a horizontal asymptote on the x-axis, or at y equals 0. So y equals 0 is a horizontal asymptote. And I can also see here that I have vertical asymptotes at x equals -2 and at x equals +2. And those vertical asymptotes are a clue about my equation. I know if I have a vertical asymptote at -2, then x plus 2 must be a factor of the denominator. If I have a vertical asymptote at +2, at x equals +2, then I must have x minus 2 as a factor in the denominator. And if I have a horizontal asymptote, it must be true that my denominator has a larger degree than my numerator. Denominator right now is degree 2. So I want the numerator to have degree 1 or degree 0. I'm not quite sure yet. I'm just going to make a guess and put a 1 here, adjust it if we need to. So we can now try plotting some points. Let's see what happens when we let x equal 0. If x is 0, I get -1/4. And on the graph, when x is 0, I'm at this point right here, which does look like it's about -1/4. Let's see what happens when x is 1. If we let x equal 1, we get -1/3. 1, -1/3. And that does look like it's about -1/3 right there. So I think I've found the right equation. Now the domain for this function is all real numbers except those 2 points where I have vertical asymptotes. So all real numbers except -2 and 2. We can simply just write x is not equal to -2, x is not equal to +2. Or if we wanted to do interval notation, we would say -∞ to -2, union -2 to +2, union 2 to infinity. The range is all real numbers except where I have that horizontal asymptote. So all real numbers except 0. I could say y not 0. Or if I wanted to do interval notation, I would say -∞ to 0, union 0 to infinity. And the graph for h. Now this one looks like a square root function or a radical function. And if you remember what y equals square root of x looks like, the shape of the graph looks just like this. So I'm guessing this one has just been shifted left and up. It doesn't look to me like it's been stretched. Maybe it has, so we can check that. So if it has been shifted, so on the parent function, this point here is normally at the origin. So it looks like we've shifted left 2 units and up 1 unit. So that would be y equals square root of x plus 2, that would shift it left 2, and then plus 1 on the outside is going to shift it up 1. Now we might have some type of vertical stretch here, so there could be an a value. I left a little bit of space after the equal sign just in case. What I'm going to do is plot these extra points and see if I need to adjust this equation. So I have this point -1, 2. When x is -1, let's substitute that into our equation and see if we get 2 for y. So when x is -1, I get the square root of 1 plus 1, which is 2. That checks out. This other point here, 2, 3. When x is 2, let's see if we get 3 for y. When x is 2, I have square root of 4 plus 1, which is in fact 3. So both of these points check out. I guess I can check this initial point here as well, which is at -2, 1. When x is -2, we get square root of 0 plus 1 is 1. So all 3 points check out. This is my equation for this graph. Now the domain for my function, we're going to include -2, and then it goes to infinity from there. Range, we're going to include 1 and goes up to infinity from there.